Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson for chemical engineering thermodynamics, we are going to be still looking at Chapter 3, which is volumetric properties of pure fluids. And we are looking at ideal gases, and we have a few examples that we're going to look at today. So the first of these is really just a matter of how do you know whether or not something is an ideal gas? Now, we will later be talking about ways that you might predict this, but for now, we know that it's an ideal gas because it behaves like an ideal gas. And what does that mean? It means that it follows the ideal gas law. So in this example, we have water at 2600 degrees Fahrenheit, so a very high temperature, and 20 psia, which is a high pressure compared to atmospheric, but it's not very high. And it has a measured specific volume of 91.132 cubic feet per pound mass. And what we want to know is, could this be considered to be an ideal gas or to behave as an ideal gas? And for this particular case, we can use R for water as 85.76 foot-pound force per pound mass degree R. Now, the recommended way to approach this is just say, well, what if it does behave as an ideal gas? So in that case, I'm going to use the ideal gas law. And plug numbers in. Now, be careful that you are using units with this because they can trip you up a little bit. So 85.76 foot-pounds force per pound mass degree R. The temperature given is 2600 degrees Fahrenheit, so I can correct that by adding 459.67 to degrees Fahrenheit, gives me degrees Rankine. And the pressure, and being sure again that it's absolute pressure, is 20 psia. It's convenient to correct this so that I know really what the units are. It's pounds force, not pounds mass, per inch squared. Okay, so if I do this, I see that my pounds force are going to cancel. My degrees R will cancel. I have feet over pound mass and inch squared. Okay, so this is very confusing units. And you can look up unit conversions. There's, lots of ways you might do this. Probably the most logical would just simply go inches squared to feet squared. But what I looked up when I did it is I was like, oh, these pressure units are not what I want. And so 14.6959 pounds per inch squared is the same as 2,118 pounds per foot squared. Now again, I could have gotten exactly the same place using a conversion from inches squared to feet squared. But now then, my inch squareds will cancel. I'm left with feet squared, which cancels, I'm going to end up with 3 of these in the numerator. And so V is going to be 91.154 cubic feet per pound mass. Okay? And that's really very close to the measured volume, specific volume. So therefore, my conclusion is, yes, I could consider this to be an ideal gas. So now my question is, does water always behave as an ideal gas? So let's look at a different set of conditions. So water's at 800 degrees Fahrenheit, still a high temperature, but not nearly as high. And my pressure, instead of being 20, which is near atmospheric, I've now gone up to 10,000 psia. And in this case, the measured value of V is 0.02765 cubic feet per pound mass. So we can repeat the calculation. And there's not going to be anything really that changes, so therefore I'm going to write in my numbers without units, trusting that my work with units is fresh enough that I remember and believe it. And in this case, I get 0.07507 cubic feet per pound mass. Okay, that's the ideal gas prediction. This is the actual value. So no, in this case, this is not behaving as an ideal gas. The lesson here is that just because something is behaving as an ideal gas under one set of conditions does not mean that it always does. Kind of rule of thumb is that higher temperatures help and lower pressures help. So in this case, I lowered the temperature and I raised the pressure. And so this went to being something that was most definitely not an ideal gas. Now we will, like I say, be coming up with some ways that I can do a more predictive job of whether something is an ideal gas rather than having to wait until I calculated a value and compare it to a measured value. So now let's do an example where we work with our definitions of energy that we've been working with in this chapter. In this case, we have an ideal gas. So I'll write my given information. So I'm told that it is an ideal gas. It's in a well-insulated, so Q is 0, piston cylinder, so that means it's closed and has moving boundary, so I can expect work not to be 0. So I get all of this from the fact that it's a piston cylinder. It's initially at 1500 Kelvin, so T1 is 1500 Kelvin. P1 is 200 kilopascals. And the piston moves, expanding the volume until P2 equals 50 kilopascals. The gas has gamma, which remember is C sub P over C sub V, is 1.3. And the process efficiency is 80%. We'll write it as a decimal. And we want to know how much work the fluid does. Okay, so we want to find the work. Now in this case, this is expanding, which means it is pushing on the surroundings. So therefore, I expect that work will be negative because it is leaving the system and going to the surroundings. It's pushing on the surroundings. So I'm going to expect a negative answer based on the way the problem statement was made. And that's going to give me a way of checking how well I match. Okay, so now then, we want to know the work. I know that it's got an efficiency of 80%, so this means I'm looking for real work, but I can't just directly calculate that. What I need to do is calculate the amount of reversible work. So the work for the reversible process is going to be this negative integral of P dV. In this particular case, they told me that I have an ideal gas with constant gamma. It's 1.3. Therefore, this is polytropic. And so I can use one of those expressions that we had in the previous video. In this particular case, data I have is temperatures and pressures. So the form of the equation that I want to use is RT1 over gamma minus 1 times P2 over P1 to the gamma minus 1 over gamma power, all minus 1. And if I plug in values for this, then R is 8.314 kilopascal meter cubed, or I can use kilojoules, your choice. And you'll find that kilojoules will be more convenient, but not usually what you look up. Kilomole Kelvin. So 8.314 kilojoules per kilomole Kelvin times 1500 Kelvin all over 1.3 minus 1 to the P2 over P1. Now in this case, just be sure you're using absolute pressure and that they have the same unit. So P2 is 50, P1 is 200, to the 1.3 minus 1 over 1.3 power. Subtract 1 from that answer. So when I do this, I get that the work for the reversible process would be negative 11,382 kilojoules per kilomole. So this is specific work. And if we take the standard that we're going to write our answers between 1 and 1,000, then this is negative 11.4 megajoules per kilomole. Now this is the ideal, this is not the actual. So we don't want to stop here. We want to take the next step. The real or the actual or the irreversible amount of work is going to be 0.8 times that. Negative 11.4 equals negative 9.11 megajoules per kilomole. So that's our answer. I want you to start paying attention to when we do problems where we talk about real versus reversible, because as we move into chapter 5 and start talking about the second law, what you're going to start noticing, and probably you've noticed this just in your real life, is that the actual amount of work you are able to do is less than what these ideal model predictions will tell you. Okay? And that's going to just kind of be a general truth. And we're going to be talking about that very soon, as I say, in chapter 5 for this textbook. So this concludes this video lesson. Next we'll be looking at virial equations of state. Thank you very much for your time.